Okay, Chapter 5, Section 5, the substitution rule. Okay, so we know so far that if we want to find the integral from a to b on cosine x dx, then we have to know how to rewrite the cosine as a derivative of a function. That way we can use part 2 of our fundamental theorem of calculus and be able to simplify it. So kind of on to the side, we think about derivatives, we think about antiderivatives, and maybe we remember that the derivative with respect to x on sine x equals to cosine x. Therefore, the antiderivative of cosine x, or backwards, well, it's got to have something to do with sine x, except we have to think about constants, right? So this is the general antiderivative. All right, so keeping that in mind, we know that to solve this one, then we could say, well, okay, it's the integral from a to b on the derivative with respect to x of sine x dx. The derivative of sine x is cosine x. And now these two kind of undo each other. And so we could say that this is going to be equal to sine x evaluated a to b, or just sine of b minus sine of a. Okay, so this is using part 2 of the fundamental theorem of calculus, makes life easy. And really the hard part is this, knowing that the cosine of x can be rewritten as the derivative of sine x, right? That's the antiderivative. For some of the more straightforward ones, then we can just kind of refer back to our chapter 3 work with derivatives, so we can kind of go backwards and figure out what that function would be. But not every integral can be solved that way. Consider the following. Okay, suppose we're tasked with finding this indefinite integral. So this antiderivative. Find a function whose derivative equals to this. There isn't anything that comes to mind right away. There isn't any function that comes to mind right away as one of our standard kind of functions, such that its derivative equals to this. So we're going to develop a new idea here, a new technique to help us with these sorts of things. And the idea is to substitute the variable x with a new variable. Usually we like to use the letter u. And so I'm going to let u equal to 1 plus x cubed. Okay, so now what I want to do is replace all of these variables with u, right? This indefinite integral is written in the variable x. I want to rewrite it so it's written in the variable u, all of it. So I have to be real careful how I do it, because I also have to replace this dx and rewrite it with a du. So I'm going to let u equal to 1 plus x cubed, and now I'm going to take the derivative with respect to x on both sides. So d dx of the u is equal to d dx of the 1 plus x cubed. Okay, on the left-hand side, well, I'm just going to rewrite this as du dx. And on the right-hand side, well, now I can take a derivative because it's with respect to x, and this function's in x. And that's just going to be 3x squared. Okay, I'm going to multiply both sides of the equal sign by dx. dx. And then here, these guys cancel. And so I end up with du equals to 3x squared dx. And there it is, 3x squared dx. So I'm going to copy this over here to make some space. So this is the integral of, and I'm just going to swap these two around. Right, so I'm going to write down the root first, 1 plus x cubed. One plus x cubed times, and then 3x squared dx. And now this portion inside the root, that's my u, it's this guy. And this whole thing, including the 3x squared, including the dx, all of that is equal to my du from there. Good. So that means that this indefinite integral can be rewritten in u now as the integral of u du. Okay. Now this one's an easy one to find. I can just rewrite this as u to the 1/2 power du. And we know that this is going to be equal to u to the power of 1/2 plus 1, and then 1 over 1/2 plus 1. And then that can be simplified. Zoom out a little bit. That can then be simplified as 1 over u to the, this is going to be 2 over 2 makes it 3 over 2. Means that this is going to be 3 over 2. Multiplying the numerator and the denominator by the reciprocals gives me that this is equal to 2/3 u to the 3 over 2. And so I did find the antiderivative of this function. In u, of course, the original one was written in x. So now what I have to do is say that the question I really wanted is going to be equal to this one, where I resubstitute the u, which is equal to 1 plus x cubed. So my final answer then is going to be that the antiderivative of 3x squared, square root of 1 plus x cubed dx, is equal to, and I'm just going to copy this thing, which is going to be 2, 3 parentheses, and then instead of a u, I'm going to go back to x as 1 plus x cubed. That's my u. And then all of it gets raised to the power of 3 over 2. Good. So there's my final answer. And I can check it quite easily. Check. If it's in fact true, if I really did find the antiderivative, it must be true that the derivative of this thing equals that. Oh, of course, this must represent a whole family of a family of functions. So I have to, I almost forgot to include the plus c there. So there has to be a plus a constant as my most general answer. Right? And I can check it because if I take the derivative of this function, I should get that one. And the c could be anything. So for example, let c equal to the number 3. That means that the derivative with respect to x of 2/3 1 plus x cubed to the power of 3 over 2 3 over 2 plus c. So let's say plus 3. This is where c equals to 3. This derivative is then going to be equal to 2, 3 times 3 to 1 plus x to the 3rd power, to the power of 1/2, times the derivative with respect to x of the inside, thanks to the chain rule, 1 plus x cubed, which gives me, okay, these guys cancel. I end up with 1 plus x cubed to the power of 1/2 times, and then this becomes 3x squared. Remember, notice that the derivative with respect to x on the number 3 is just 0. So I could have just included an extra 0 out here. Plus 0, right? But it doesn't count, so I just leave it alone. And then I can just mix this around a little bit and confirm that we get 3x squared and then the square root of 1 plus x cubed, which is exactly what we expected. 3x squared plus, times the square root of 1 plus x cubed. Right? So indeed we've confirmed that this is a function such that the derivative of this function equals to that. Okay, so this is the general layout for this method called the substitution method. We're going to have an integrand that's going to be kind of ugly, kind of complicated. We're going to choose the right value for u, and that can be kind of the hard part. How do you choose which value of u is going to work? That's when a little bit of practice and experience pays off. But when you choose the right value for u, then you take the derivative with respect to x on this u, and then you can solve for du. And then we come back, hopefully we can do a nice substitution and be able to find a new integral written in the letter u, such that that integral is easy to find. That's our goal, at least. So in general, this method works whenever we have an integral that can be written in this form. So it's the integral of f of, so this is a composition of functions. So the g of x is inside the argument of the x function. So let me put it in parentheses like that. So this is f of this function times g prime of x dx, right? Remembering our chain rule. So note that if, observe that if capital F prime equals to lowercase f, then the integral of capital F prime of g of x times g prime of x dx is equal to capital F g of x plus some constant, right? Meaning that if we take the derivative of this guy here, thanks to the chain rule, we would get this. It's the derivative of the outside function, capital F prime of g of x times the derivative of the inside part. Okay? If we make a change of variable or a substitution of letting u equal to g of x back up here, so we replace this with a u, then this gets replaced with a u as well. And so we get that the integral of f prime g of x times g prime of x dx is equal to capital F of g of x plus a constant. And now we replace that g of x with a u. We get capital F of u plus c, which is equal to the integral of capital F prime of u du. Or writing f prime equal to f, we get that the integral of f g of x times g prime of x dx is equal to f of u du. Okay, so here's the formal presentation of our substitution rule. Okay, so the substitution rule, if u equals to g of x is a differentiable function whose range is an interval I and f is a continuous function on I, then the integral of f of g of x times g prime of x dx is equal to the integral of f of u du. Okay, so this allows us a technique that lets us take an integral that will probably be very confusing, very difficult, very convoluted, and if we find the appropriate value of u, we can rewrite it into a new integral expressed in the variable u that will hopefully be a little easier, right? And all of this is made possible by the chain rule. Right? So another way of kind of thinking about this is to kind of begin by the chain rule, recall the chain rule. Recall that if I have some capital F function of u, and I want to take a derivative with respect to x on the function f capital of u, then this is f of u, like this. We want to take this derivative. Then what we do is we take the derivative with respect to u on f of u, and then thanks to the chain rule, well, now what we got to do is we got to take the derivative with respect to x on that u function. Okay, so this is really capital F prime of u, the derivative of the u, times the d dx of the u. Good. So if you run into something that happens to fit this form, then you can use the chain rule to establish it like this, so you can rewrite it in terms of u. Okay, so say we were asked to find this antiderivative, this indefinite integral, x to the 5th power times sine of 3 minus x to the 6th power dx. Okay, so what we want to do is let u equal to this part here. And the reason I want to let it be that part is because I'm already thinking ahead that I'm going to have to find the derivative of u, so I can do my substitution, my replacement of all the variables, including the dx. And I can see that that will have something to do with power of 5 when I take its derivative, and that's what that's out there. So let's let u equal to 3 minus x to the 6th power. Now when I take my derivative with respect to x on the left-hand side, the derivative with respect to x on the right-hand side, I end up with du dx equals to negative 6x to the power of 5. And that's really close to what I have already, right? So multiply both sides by dx, 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 cancel, cancel, and I end up with du is equal to negative 6x to the 5th power times dx. Okay, so now coming back up here to this one, I'm going to copy it again. I'm going to just switch around the order of the function. We have sine of minus x to the 6th power times x to the 5th power dx. Right, so all I've done so far is just switch around these guys. I just wanted to put my x to the 5th power right next to my dx, because that's what I have here. So all I'm missing is this minus 6. Well, just put it in there. Minus 6 times that. Now, of course, you can't just go around multiplying things by minus 6, but here's what you can do. Let me erase that. What I could do is multiply it by a negative 6 over negative 6. Right? Negative 6 over negative 6 is just another version of 1. And multiplying anything by 1 doesn't change the value. So this one time, to be really, really clear, I'll just start by saying, let me multiply it by 1. And then, so that doesn't change anything, right? I just multiplied it by 1. And then I'm going to multiply this by minus 6 over minus 6. That's another version of 1. Integral sine of 3 minus x to the 6th times x to the 5th dx. And then I'm going to put that one over there. I'm going to switch it around. So I'll end up with the integral of sine of 3 minus x to the 6th times x to the 5th dx times x to the 5th dx, and there's going to be a little minus 6 out there, and then a 1 over minus 6 out here. Okay, now I'm going to let this whole thing, including the sign, be careful with the sign and everything, the whole thing is exactly equal to du. And now this part in here, well, that was just my u. So I've managed to rewrite the entire integral now using the variable u. So now this is going to be equal to negative 1/6 integral of sine of u du. And that's an easy antiderivative. The derivative of cosine of x equals to negative sine. So this is just going to be equal to negative 1/6 times negative 1 times cosine of u. Good, so we're almost there. Negative, negative, those guys will reduce to give you a positive 1/6. So you end up with positive 1/6 cosine of u. Now we're almost done, except I have to come back to my original variable of x. So now as a final step, then I would say that this is 1/6 times cosine of 3 minus x to the 6th power. Good. And remember, this is the general antiderivative, so now we just got to put a plus c at the end. Okay, so just to kind of put it all together, it's this equals that, and that comes all the way down here. So I'll say that the integral of x to the 5th power times sine of 3 minus x to the 6th power dx, right, this integral equals this. That'll be my final answer. Okay, so we're going to start off with something that's going to be really complicated. Our goal is to find a way to simplify it by choosing the proper value of u such that we can rewrite the function in u and we end up with a simpler integral that we can identify, that we can work with. The trick is just to pick the right u, and the right u will be one such that when you take its derivative will be found there, right? So this question would actually be a lot harder if this portion wasn't there. For example, if the original question just had this, you'd think that that would be easier, but it's not, because when I do the u substitution, I'm missing x to the fifth power. It's not there, and that becomes more difficult, a little more challenging to work with that. Right? So it's actually kind of convenient that there's an x to the fifth there. Okay, let's try more problems. Okay, now let's consider this integral, the integral of 3x plus 1 squared. This one is easy enough to expand because it's just squared. That's not hard. And then we can use our traditional antiderivatives to solve it. So this can easily be rewritten as the integral of, and then just expanding that gets us to 9x squared. 9x squared plus 6x plus 1 dx. And now that's something we can easily solve. That's just equal to x to the third power times 1/3 times 9. That's going to give me a 3. Plus 6 times x to the second power times 1/2 gets me to a 3 there. And I'll need a plus x. Derivative of this gives me a 1. Okay, so then I can simplify that just a little bit and get, let me zoom out a little bit, and get that this is just going to be equal to 3x cubed plus 6x plus x. And of course, if I want the most general antiderivative, we have to think about also including a plus c at the end plus some constant, right? And then we can check, real quickly here, check to make sure it works. Check. Well, actually, let me combine the first statement and the last statement so we can box it up. So we get the integral from 3x plus 1 squared dx then is equal to 3x cubed plus 6x plus x. Wait, no, this is wrong. 3 goes into 9 3 times, 2 goes into 6 3 times, and we have an x squared. So this should be, copied this wrong. This should be 3x squared. 3x squared plus x. Good. So let me erase this over here as well. It should be 3x squared plus x plus c. So there's our antiderivative, our indefinite integral. And we can easily check, because if I did a good job, it should be true that the derivative of this equals that. Right? So the derivative with respect to x of 3x cubed plus 3x squared plus x plus some constant c, it must be true that its derivative equals that. So that gives me 9x to the second power. Breaking down the 3 gives me a 9x to the second power plus 6x to the first power plus 1. And we just saw that that's this. So this equals to 3x plus 1 squared. So we're happy. Worked out. Okay, this is an example where we can just expand it all out and get our answer that way. But we want to use a different method, the u substitution. And I'm using this power of 2 here because this way we can compare the two and hopefully get the same answer. But the value of the u substitution is that it will allow me to increase this power to much higher numbers or fractions, and we'll be able to still integrate it, whereas this method might run into problems. So for example, I'll put a big or. If I come down here and do the integral, and now I'm going to use the u substitution method, squared dx. Let's scroll down here. Okay, so I'm going to let u equal to this part. Let u equal to 3x plus 1. The derivative with respect to x on the u is then going to be equal to ddx of 3x plus 1, which gives me that du dx equals to just 3. Right? The derivative of 3x is 3. The derivative of 1 is 0. So du equals to 3 dx. almost what I need. So I'm just going to come back over here, and I'm going to rewrite this as 3x plus 1 squared dx, and I'm going to insert the value I need. I need a 3 there. I'm going to balance it out with a 1/3 out there. That way I'm really just saying it's another version of 1. I haven't changed anything. Okay, so then this is going to be my du, and the part inside here is going to be my u. I've managed to rewrite my integral into something that only involves u to the second power du. And that should be really easy to find. That's just going to be equal to 1/3 times, and this is going to be equal to u to the power of 3 times 1/3. The derivative of this gives you u squared. Good. So this is going to be equal to 1/9 u to the third power. Now we substitute our u value once again and say that this is equal to 1/9 3x plus 1 to the power of 3 plus some constant. Okay, so let me write that down over here and box it up. The integral of 3x plus 1 squared dx is now also equal to 1/9 3x plus 1 to the power of 3 plus some constant. Okay, so two methods that lead to two answers. And maybe at first it's not extremely obvious of why they're equivalent, but they are. If we expand this, we end up with 1/9, and then expanding this right here will get us to the following: 3x to the power of 3 times 1 plus 3 times, and then it's 3x to the power of 2 times 1 to the power of 2 plus, and then 3 times 3x to the power of 1, and then 1 to the power of 3. And finally, wait, no, I messed up. This is to the power of this guy are off from there. I'll write down the pattern 1 second. So that's going to be 1 times, and then this is going to be 1 power. Well, you know what? Let me include it just to include the whole pattern. It's going to be 3x to the power of, and then 1. Okay, so I'll put them in color. Okay, so thinking of Pascal's triangle, I'm thinking of 1, 1, and then 1, 2, 1, right? Add those two to get the middle one, and then 1, 3, 3, 1, and then 1, 4, 6, 4, 1, and then you can just keep going. So this one deals with powers of 2, and then this one helps us with powers of 3. Okay, so this is how I know that there's going to be a 1 out here. So 1, it's this 1 right here, and then a 3, and then another 3, and then there's going to be another 1 out here. So these are the constants that are part of this expansion. 1, 3, 3, 1. Good. Then I copy this term. Let me put it in blue. Well, no, it's. Then this term right here gets copied, and this term gets copied. So 3x times 1, 3x times 1, 3x times 1, 3x times 1. And then we write down powers starting with 3 and do a countdown. So 3, 2, 1, 0. And then the other direction, which would be 3, 2, 1, 0. Remember that 1 to the 0 power is just going to be 1. And 3x to the 0 power is also just going to be 1. Okay, so this will simplify a little bit to 3x to the power of 3. That's going to be 27 x to the third power times 1. Plus, this will be 9 times 3 gives me 27 x squared times 1. plus, and this gives me 1 squared, that's going to give me 9x, plus, and that's just a 1, that's a 1, that's a 1, so plus 1, the whole thing. Now we distribute that 1/9 everywhere, and we get 3x to the third power plus 3x squared plus x plus 1. And if we compare it now with the previous answer, now it should look a little more familiar. (3x cubed plus 3x squared plus x). It's all the same terms. And there's a plus 1. Well, that's okay. Remember, there's also a plus c. So there's a constant. Constants don't matter. Right? So the plus some c value. Good. Well, maybe that c is -1. Therefore, it cancels out, for example. Right? Point being that the derivative of this function is going to be equal to this function. Right? Just like we saw before, it doesn't matter what that constant is. The derivative of that constant is going to disappear. Okay, so we've confirmed that we have 2 ways of finding this answer. Okay, so we've solved the same integral in two different methods, and so that helps us confirm that the method of substitution works. It gives us the same answer that we would have gotten if we just expanded it all out and used our prior indefinite integral formulas and patterns to solve it. But the advantage of the U substitution is that it makes it possible for us to work with situations where the exponent is much uglier. So, for example, consider what would have happened if instead of a nice, easy little squared there, we had a different power, like maybe it was raised to the power of 9. Ooh, well, that would be hard to do it this way, right? Expanding this all out would be a real nightmare. We could do it if we had a lot of time and you just really want to do it. We could expand it all out and then find the antiderivative of each one. But it would just be a lot easier to do it this way. Also, we don't have to have a whole number. If we had 9 divided by 2, for example, that would be hard to explain how to expand it all out. That gets kind of ugly. Whereas it makes a lot of sense, or it's just a lot easier to do it this way with the substitution method. So the substitution method allows us to do things that are a lot more complicated, and that's why we want to get comfortable with it. Okay, let's try another one. Say we wanted to solve this now. The square root of 3 plus 2x squared times x to the 5th dx. Let's begin by letting this part be the u. So we're going to let u equal to the 3 plus 2x squared. Okay, so next we want to take the derivative with respect to x. dx of the u equals to d dx of the 3 plus 2x squared, which gives me du dx equals to, okay, the derivative of 3 is 0. And the derivative of this one is going to be equal to 4x. So du is equal to 4x dx. Okay, so then coming back over here, I'm going to rewrite this. I get the integral of the square root of 3 plus 2x squared. And now I have an x to the 5th, but I only need one of those x's. There's 5 x's there. I only need one of them to substitute my du. So I'm going to break it up. I'm going to separate the x to the 5th into x to the 4th power and x to the 1st power. That gives you 5 x's. And then I'll have my dx as well. So I'm almost there. I'm just missing that 4. So I'm going to multiply this by 4 and then balance it out with a 1/4. Now I can say that these two things equal each other. And I'm ready to do my substitution for du. And I'm ready to do my substitution here for my u. But what am I going to do with that x to the 4th power? Right, so this is my u. And this whole thing is my du. what about this guy? Right? That's a bit of a mystery. It's not part of this, and coming up here, it's not part of that. So what I want to do is solve for x squared from here. So I'm going to take this, u equals to 3 plus 2x squared, and solving for x squared gets me u minus 3 equals to 2x squared, subtracting 3 from both sides. Dividing everything by 2, we get u minus 3 divided by 2 equals to x squared. And now this is what we use to replace that. Right? So now if I square both sides, I get u minus 3 divided by 2 squared equals to x squared squared, which means that u minus 3 divided by 2 squared is equal to x to the 4th power. And now I can rewrite my x to the 4th power. Now I'm ready to do a substitution. This is going to be 1/4 integral of the square root of u times, and now this whole thing, which is going to be equal to u minus 3 divided by 2 squared du. So initially that seems like I exchanged an ugly complicated integral in x into an ugly complicated integral in u, but this one's a little bit more manageable. So let's fix it a little bit. This is the same thing as 1/4 integral of, and I'm going to rewrite the u as u to the 1/2 power, parentheses, u minus 3 squared du, and there's a 1/4 there, so I'm going to throw in, well, okay, you know what, I'll do it in 2 steps. I'll put a 1/4 there, and I'm going to bring it outside. So there's really going to be 1/16 integral of, and I'm going to go ahead and expand that. That'll be u to the 1/2 times u squared minus 6u plus 9 du. And now if I distribute this u to the 1/2 power, I'll get 1/16 integral of u to the power of, remember we add the exponent, so that should be 5/2, or 2.5, minus 6 u to the power of 1.5, which is going to be 3/2, plus 9 u to the 1/2. And all of that is du. And now we can just use our power rule to find these antiderivatives. This is going to be 1/16 times, and then I know I add 1 to the exponent, so this would be equal to u to the power of 7/2. And then I balance it out by multiplying it by 2/7, minus 6 times, and this is going to be u to the power of 5/2, and I balance it out by multiplying it by 2/5, plus 9 times u to the power of 3/2, and again I balance it out by multiplying it by 2/3. Right, so a quick check then, if I bring this down, when I take the derivative, I bring the exponent down as a factor, everything would cancel, subtract 2/2, I get this term, that works out. Then if I bring this 5/2 down, it'll cancel with this 2/5, subtract 2/2, I get 3/2, that works out. And if I bring down the 3/2, cancels with this term, subtracting 2/2 gets me to that term. Okay, good. So this, the derivative of this function equals that function. All I have to do is simplify it a little bit. Well, that doesn't reduce, but 3 goes into 9. 3 goes into 9 3 times. And so I'm ready to rewrite this up here. Come up here. Okay, I'll just write it underneath here. So this is going to be equal to 1/16 times 2/7 u. Now u was equal to 3 plus 2x squared raised to the power of 7/2. Let me erase this thing. And then this doesn't reduce, so that'll be 12, so minus 12/5. and this will be 3 plus 2x to the second power raised to the power of 5 over 2 plus 6u, which again, let me zoom over here. This is equal to 3 plus 2x squared raised to the power of 3 over 2. And then all of that gets multiplied by this 16. So now if we just distribute this 1/16 across, we'll be at a pretty good place. So this is going to be equal to 2 reduces with 16, 8. We get 1 over 56. 3 plus 2x squared raised to the power of 7 divided by 2 minus then 1/16 times 12, that will have a 240. 2 gives me a 6 divided by 8 times 4 makes it 40. Oh, and that also reduces. Oh, so 4 goes in here, 4, 20, and 3. So this one's a 3. And then this one is going to be 3 plus 2x squared to the power of 5 over 2 plus, and then 16 over 6. 2 goes into both of them, gives me a 3 divided by 8. And then this is a 3 plus 2x squared raised to the power of 3 divided by 2. And so now if we just put our constant, we'll get our final answer there. Okay, zoom out. And so let me copy this guy over here. So this is the integral of 3 plus 2x to the power of 2, square root of that whole thing, times x to the 5th dx. Okay, so the real, the new idea here is this one. This is a very useful little trick when you're doing your substitution. Sometimes you got to go back to your u and solve for x, so you can come back and completely substitute all the variables from your original integral into something that only has u's in it. Cool. All right, moving on. So far, we've only been working with the substitution rule when it comes to indefinite integrals or antiderivatives, but a similar rule can be applied to definite integrals. So now we have definite integrals, so the integral from a to b on f of g of x times g prime of x dx is equal to the integral of g of a to the equal to the integral from g of a to g of b of f of u du. Good. All right, let's see how this is implemented. All this really means is that we also have to be careful with the limits of integration, and we either have to substitute, find a new value of our limits of integration under the consideration that u equals to some function g of x, or we have to be careful not to evaluate it until we resubstitute the u back in terms of x. Let's look at some homework problems. Okay, so looking at the homework problems on 5.5, over here we have a lot of indefinite integrals. And now let's try some definite integrals. How about we start off with something easy like, say, number 56. Okay, so let's let u equal to 5x plus 1, and then its derivative, d dx on u equals to d dx on 5x plus 1, which means that du dx equals to just 5, and now du equals to 5 dx. Okay, so that's going to be a very straightforward substitution. So then bringing this over, I'm going to rewrite this as 1 over 5x plus 1 times the dx. And then I know I'm going to need a 5, so I'm going to introduce that 5 in there and balance it out with a 1/5. Oops. Balance it out with a 1/5 as I did before, but we have to pay attention to the limits of integration. One thing I would do if I was the author of this book, if I can contribute one thing to calculus, is that I wouldn't leave these alone like this. I would express them, define them, and say that this is when x equals to 0, and this is when x equals to 3. Right? Make it really super obvious what those limits of integration are referring to. So if I just put a 0 and a 3 here, it might not be super clear what that variable refers to. So this is x goes from 0, x goes to 3. Good, so now when I do my u substitution, I'm going to replace this whole thing with a du, and I'm going to replace this denominator with a u, but I also have to think about those limits of integration. You have two options, really. The first option is to also replace those limits of integration by using this formula. So let me do that one right now. So when x equals 0, then we let u equal to 5 times blank plus 1. And, well, I should have put it in green. When x equals to 0, put a 0 there. And so u becomes 1. U becomes 1. Okay. When x equals to positive 3, then u is equal to 5 times blank plus 1, using that same rule. So there'll be a 3 in here, and so u becomes 16. U equals to 16. And so now we're ready to do our complete transformation. This equal that, and now we're going to say all of that is equal to 1/5 on the outside, integral, as u rate changes from 1 to u goes to 16, on the integral of 1 over u, and then this is just going to be du. Good. Okay, so now this is something that we remember, something whose derivative is equal to 1 over u. That's going to be 1/5 times, and it's going to be ln of absolute value of u, evaluated as u ranges from 1 to 16. Good. So this is just going to be 1/5 parentheses ln of absolute value of 16 minus ln of absolute value of 1. Now, because 16 and 1 are both clearly positive numbers, we don't need the absolute values anymore. And the ln of 1 is 0, so that just disappears. And so this becomes 1/2 ln of 16. And then we can rewrite the 16 as an exponential number, 2 to the power of 4. This is equal to 1/2 ln of 2 to the power of 4. And our log properties tell us we can move that 4 out in front. So this becomes 1/2 times 4 ln of 2. And the 2 and the 4 reduce to give me a 2. And that'll be my most simplified answer, 2 ln 2. Okay, so let me come back here and rewrite the whole thing. So therefore, the original integral, the integral from 0 to 3 on 5x plus 1 dx is equal to 2 ln of 2. Okay, now the other option, very, very similar to this, would be to do the same beginning. Let me zoom out a little bit. would be to do the exact same beginning here. So from here, I'm just going to go over here and copy that over here and say that that's option 2. Option number 2. This one was option number 1. Actually, okay, so option number 2 is going to be to leave this alone, leave the limits the way they are, and just change the rest of it. So I'm going to rewrite it as 1/5 integral, and then I still have the 1 over u du. So that stays the same. But instead of doing this, where I change the limits integration back to the variable u, I could leave them in terms of x. So just, this is the more dangerous option because people make mistakes if they lose track of the fact that these limits belong to the x variable. Okay, so then we would find our results. Okay, so this is 1/5. This is going to be equal to ln of absolute value of u evaluated from, and now this is where you have to continue to be careful. This is for x goes from 0, x goes to 3. So a mistake right now, very common mistake doing it this way, is for people to say that the answer is going to be ln of 3 minus ln of 0. That's wrong because this is the x variable and this is in terms of u. So we still have to come back and replace our u back to this formula. Okay, so don't do that. So now we come back up here and we go, this is equal to 1/5 ln of absolute value of, and then we replace that u with 5x plus 1. Evaluate it as x ranges from 0 to 3. And now we can plug in the x value of 3 and 1. This is going to be equal to 1/5 parentheses ln of absolute value of 5 blank plus 1 blank minus ln of absolute value of 5 blank plus 1 blank. And now we can plug in a value of 3 here and a value of 0 here. And now we're going to get the exact same answer as before. 1/5 ln of 16 minus ln of 1. And so that's going to be that answer up there. And after a little bit of massaging, we see that we're going to get the exact same result. Right? After a little bit of work, we'll get that this is equal to the 2 ln 2, just like before. Okay, so 2 options. They're both good. You just got to keep track of which one makes most sense to you. Sometimes in some equations, it might make a lot more sense to change the limits of integration, like this one. Might make the whole problem a lot simpler to do it that way. And in some cases, it just might feel more convenient to solve it, and you leave the limits in terms of the variable x, and then come back and replace that u value. So it's totally up to you. You can do it either way. Just be real careful not to make the mistake of plugging in 3 into this point here, ln of 3 minus ln of 0. Okay, let's try one more. How about number 62? Okay, so we have cosine x times sine of sine x. So I think it would make sense to try and let u equal to this so that we can simplify this composition of functions a little bit. And if we let u equal to sine, its derivative is cosine, which is right out there. So that feels like the right thing to try. If you pick the wrong u and it doesn't work out, then come back and try something else. So let's let u equal to sine of x. Therefore, dx of the u is equal to d dx of the sine x, which means du dx is equal to cosine x. So du equals to cosine x dx. So the cosine x dx is right there. Now I'm going to change my limits of integration. So this is going to be when x equals to 0, I have that u equals to sine of 0. Sine of 0 is 0, so u just goes to 0. That was easy. When x equals to pi over 2, u equals to sine of pi over 2. Sine of pi over 2 is equal to 1, so u equals to 1. Okay, so now I'm ready to make my substitution. And I'll say that this is going to be the integral, and I'm still going to keep my x here. This is x goes from 0, x goes to pi over 2. And I'm going to switch these around. This is sine of x times cosine x dx. So this is going to be my du. Cosine x dx is my du. And then this is going to be my u. And I already have my limits of integration changed. So I'll say that this, now when we go back to u's, now this is going to turn into a u goes to 0, u goes to 1, and then sine of u du. Good, and that's easy to find. This is going to be cosine of u. The derivative of cosine is negative sine, so we have to introduce an extra minus 1. Evaluate it as u goes from 0 to 1. Good, so I can just plug in those values and get that this is negative 1 times, and then this is going to be cosine of 1 minus cosine of 0. So I'll put, well, just to be consistent, I should have kept going with my u. This is u goes from 1 and u goes to 0. Okay, so then now we replace the u with a 1 here and the u with a 0 there. Cosine of 0 degrees is equal to 1. So let's put cosine of 0 is 1. And cosine of 1, well, there's nothing, it's not an easy one. We can use a calculator to approximate it, or we can just leave it alone. It's cosine of 1. So this becomes 1. This becomes 1 minus cosine of 1. And that's as good as it gets as far as an answer. So let me just unite it all together. This is the integral from 0 to pi over 2 on cosine of x times sine of, and then there's a sine of x inside the argument of the sine, dx. And the answer is just going to be 1 minus cosine 1. Okay, so just be real careful with which value you use for your u substitution. Carefully take a derivative. If you're going to go with the method of replacing the limits of integration, then you got to take the step of evaluating your new values of u using your formula, the formula that you used. Make sure you replace every little bit of the original integral that was written in x in terms of u. Sometimes you might have to go back to this definition and solve for x, and that might help you make your substitution. Okay, now let's visit an issue of symmetry. So the following theorem uses the substitution rule for definite integrals to simplify the calculations of integrals of functions that possess symmetry properties. Okay, so suppose f is continuous on negative a to a. So if f is even, it's an even function, that means that f of negative x equals to f of x, right? Even means it's symmetric about the y-axis. It's a mirror image across the y-axis. So if we want to integrate from negative a to a on f of x dx, that's equivalent to integrating from 0 to a on f of x dx and doubling it, right? Because even functions are a mirror image about the y-axis. So we can just do half of it, find the integral of half of it, and then double it. The advantage to this is very often evaluating something with a 0 makes life really easily. Things cancel and reduce really nicely when one of the limits of integration is 0. So it's just a nice little shortcut that can sometimes work out. And then this one's a really great shortcut. So if f is odd, it means that f of negative x equals to negative f of x. Good. So odd functions, if we think about the graph, we'll see a graphic in a second, are going to be a situation where the area to the left and to the right, straddled around the y-axis, are going to be equivalent, but of opposite signs. Therefore, the integral from negative a to a of f of x dx equals to 0. That might have been a little confusing. Let's look at a picture. Okay, first, the even one. If f is even, then this is what it looks like. An even function means that it's symmetric about the y-axis. It's a mirror image about the y-axis. So if you're trying to find the integral, right, again, we can interpret it in this case as the area underneath the function, since everything is positive the way it's pictured here. So if you want to find this whole area here, then what you could do is say, well, let me just find the area from 0 to a. Let me just find this area here in red from 0 to a, and then double it, right? Because they're a mirror image about each other. And again, the advantage is that if we're integrating and one of the limits is 0, it usually makes life a lot easier. So it could be a nice little shortcut than having to evaluate the whole thing this way. Okay, this is the real prize though. This is what an odd function looks like. An odd function is a function such that if we flip it about the x-axis, right, keep that in mind, and now we also flip it about the y-axis, that those two are equivalent to each other, right? So if I flip it about the x-axis, it would look something like this, coming this way, and then coming this way, and comes that way. And then over here, this thing kind of comes this way, and then kind of comes up and comes down this way. Right? So flipping it about the x-axis, let's say there's a point here called A. If I flipped it, reversed it this way about the x-axis, that A value goes down here, like that. Good. On the other hand, if I flip it about the y-axis, that point A doesn't go there. That point A flies over here. Right? So I'll say A hat there, and then here this is A bar. Right? So either way, whether you flip it about the x-axis or flip it about the y-axis, both of those flips are identical to each other. Good. So this same red drawing would be the drawing you get when you flip it about the x-axis. It would be the same drawing you get when you flip it about the y-axis. That's the definition of an odd function. Hopefully that sounds familiar. But regardless of that, the point being here that when you have an odd function, what happens is that this area in blue is going to be symmetrically equivalent to this area here that I'm drawing in green, but clearly one of them is positive and the other one is negative. One of them is above the x-axis, the other one's going to be below the x-axis. So if you're integrating from negative a to positive a, then the answer is just going to be 0. This is a great little thing to remember because these appear in situations where the integral is just impossible to figure out. It's just really ugly. Substitution is not working. And this is when you have to pause and think back to this little situation and try and identify if this function is odd. If it's odd and you're integrating from negative a to a, then it's just a 0. Okay. All right, let's look at an example like this. Okay, so let's take a look at, for example, number 66. So it's easy to get lost in this question right away because you're thinking, okay, this is the substitution method. I'm in the section on substitutions. What do I substitute? And that gets really ugly because there's really no great choices. If we let u equal to x to the 4th power, then my du is going to be equal to 4x to the 3rd dx. And where am I going to get that? I just let u equal to this. What happens to the sign? That gets ugly right away. And they're like, okay, well, let's let u equal to sine of x. But then my du is going to be equal to cosine of x dx, and there's no cosine anywhere. That's pretty ugly too. You know, I don't know, let u equal to x. Well, then that would be du equals to dx, and then you're not going to really do anything great with it. The u equals to x, so you'll end up with u to the power of 4 sine of u du integrated from, and now we got to change the limits of integration. Oh, well, they equal to each other. So here this was x equals to that and x equals to that. And since they just equal each other, well, okay, so you've done a substitution technically, but you really haven't changed anything. U equals to pi over 3. So you're like, okay, what in the world are you supposed to do then? That doesn't work either. I let it be x, I let it be sine of x, I let it be x to the 4th. You know, it's easy to get lost. But if we pause and think about this symmetric rule, okay, so if we think about this function, the sine function obviously oscillates up and down, right? So the sine function comes up, comes back down, comes back up, and then comes back down this way and goes back up that way, right? So this is an odd function, and it's sine of x, sine of x. And what happens if I multiply this function by something that's always positive? Sometimes it's a small positive number, sometimes it's a big positive number, but it's always a positive number. Well, it's just going to kind of exaggerate or deform this, right? If it's multiplied by a small decimal that's positive, then this kind of comes up like that. And then this kind of comes down like that. And then this might come down this way, and this comes up that way, right? If I multiply the sine of x times a small positive. On the other hand, if I multiply by a big positive, well, then it's just going to exaggerate this way, and then it comes up that way, and then it comes back this way, and then it comes back down this way, and so on and so forth. Let's use technology. My drawings are ugly. Okay, so I have f of x equals, f of x equals to sine x. So there it is. I'm going to put it in blue. Here's our sine function, and hopefully we can see that this is definitely an odd function. And if I take this function and I multiply it by a constant that's positive, copy, let's make it a number that's positive, say like 3. Oops, not 33, 3. Let's make it a different color. How about green? Right? If I multiply by a number that's bigger than 1, then this is what it does to it. It makes the positive portions even bigger. Instead of the sine function reaching up to positive 1, it goes all the way up to positive 3, right? Because I'm multiplying all of these numbers by 3. And if I multiply it by a number that's definitely positive but a small decimal, like say 0.2, then it just tampers it down, and then instead of climbing all the way up to 1, it only climbs up to a height of 0.2. Okay, so that's what happens, but notice that it still keeps, it still stays as an odd function. Multiplying it by a positive number out in front isn't going to change the fact that it's an odd function. So if I multiply it by x to the power of 4, times sine of x, it is absolutely going to affect our graph, but let me zoom out. What it's going to do is that it's going to keep its symmetry. It's still going to keep the fact that it's odd. Let me see if I can come up with a good window for that. So hopefully what we get out of this is that it still stays odd. You can see when we zoom in here, this portion of the graph is still odd. And so if we zoom out, we'll still see the same thing. Okay, so this remains an odd function. And so now if we want to find the integral of this odd function from negative pi over 3 to positive pi over 3, then we know that that's going to be a really easy answer. So the integral from negative pi over 3 to positive pi over 3 of x to the 4th times sine of x dx equals to 0, right? Why? Or I should say note that x to the 4th sine of x is an odd function. based on my Desmos graph, you know, it did something like this. It kind of came up a little and then came back down, and then it comes like this, and then so it's kind of like our sine function, but then it gets exaggerated like this. And then over here, it comes down this way, and then comes back up that way, and then comes back this way, and then comes back that way, and then, right? So it's almost like our sine function, it just gets exaggerated. But it's still odd. Y-axis, x-axis. Okay, so that is our answer then. That's what's great about these if you notice them. It's an odd function. Sometimes it's hard to spot them, but then it's an easy answer. The answer is 0 because this function is odd. Okay, hopefully I've given you enough to work on your homework. So please work on your homework and stop by my office hours if you have any questions.